Hello, welcome to today's lecture. We are on chapter 7, 7.1. We're going to talk about logarithmic and exponential functions. Very well, let's take a look at the note. So first of all, recall that for ln function, if you have ln of any function like u of x, f of x, so suppose we're going to use u of x. And make sure your function is positive. So we use absolute value to make sure we have a positive function. The derivative of ln is equal to the derivative of the function or the quantity inside ln divided by the function itself. So when you take the derivative of ln function, the outcome doesn't have any ln in it. Properties of ln function. First of all, the domain of ln function is 0 to positive infinity. The domain of ln of x is equal to 0 to positive infinity. Remember the graph of ln function. When you're graphing ln function, this is your x-axis, this is your y-axis. If you have function a to the x, if you have an exponential function, and if we change the base to Napier function, this is e to the x. The inverse of e to the x is defined as ln of x. And we know that we have a symmetry with respect to the line y equals to x. So you can get the graph of ln of x. Ln of x. So as you can see, the domain of ln of x on x-axis starts from 0. It doesn't include 0, and it goes to the right-hand side to the positive infinity. So the domain of ln of x is 0 to positive infinity. As you can see, the range of the function on y-axis include negative infinity to positive infinity. The second property, when you have ln of the product of two functions, two variables, you can write this as the sum of ln of x and ln of y. When you have division x over y, it is actually the difference between their ln's. So you get ln of x minus ln of y. Note that we take the domain to be positive. So x is positive, y is also positive, x is positive, y is also positive. Another property, if your ln has a quantity that has exponent like p, you can take this exponent and write it in front of ln. So you get p times ln of x. This p can be positive, negative, but your x is positive. We talked about the derivative of ln function. So the integral of dx divided by x is equal to ln of absolute value of x plus constant of integration. Perfect. Let us go over an example to see how we can apply these new techniques to find the integral of functions. So, example on the first page. Example. Question says you have the integral of x divided by x squared plus 9 with respect to x, while your x ranges between 0 to 4. Well, we want to find the integral of this function. Remember that the integral of dx divided by x is equal to ln of absolute value of x plus constant of integration. By applying chain rule, if you have the integral of u prime du divided by u, it's actually ln of absolute value of u. Of course, we have constant of integration as well. Well, when it comes to functions in the format of a quotient function, that's something on the numerator, that's something on the denominator, and the degree of the denominator is greater than the degree of the numerator, try your best to see if you can apply this formula. Look at your denominator. Your denominator is x squared plus 9. So let u be x squared plus 9. What is du? What if I take the derivative of both sides? The derivative of x squared is 2x. The derivative of 9 as a constant is just 0. And we are taking the derivative with respect to x. Well, take a look at your numerator. Your numerator has x times dx. So if I have 2 next to my x, I can actually form my du. So let us multiply and divide the integral by 2. So my integral is now a half integral 2x dx, which is du, divided by x squared plus 9, which is u. So what do I have here? I have du over u, dx over x, which is equal to a half ln of absolute value of u. Very well. This is u. U is x squared plus 9. So you have a half ln of absolute value of x squared plus 9. And I know x ranges between 0 to 4. In the next step, we plug in 4, then we plug in 0. We try to simplify this ln function. So we're done with calculus part. The rest is just algebra. A half ln of absolute value of 4 squared plus 9 minus a half ln of absolute value of 0 squared plus 9. This is equal to a half ln of 16 plus 9, 25, minus a half ln of 9. Since 25 and 9 are both positive numbers, we can just get rid of absolute value. Well, 25 is 5 squared. You have a half ln of 5 squared minus 9 is 3 squared. a half ln of 3 squared. Remember the property of ln. If we have ln of x to the p, this is equal to p times ln of x. So we take these exponents, write them in front of ln, and you can actually see we can cancel out 2 and 2. So this is equal to ln of 5 minus ln of 3, which is equal to ln of 5 over 3. So this integral is equal to ln of 5 terms. Next page, we're talking about exponential function. So an exponential function in general is defined as y equals to a to the x. If you use Napier number, you get natural exponential function. And we know that ln is the inverse of e to the x. Very well, let's take a look at the properties of e to the x. First of all, if you have e to the x times e to the y, you can write one base and add the exponents. 2, if you have e to the x divided by e to the y, you can write e to the y on the numerator and subtract the exponents. E to the x minus 1. 3, if you have an exponential function and raise it to a new exponent, it is going to be e raised to the product of the exponents, p times x. ln and exponential function, the Napier base, they cancel out each other because they are inverse of each other. So ln of e to the x, which is equal to x times ln of e is equal to x times 1 or just x. At the same time, if you raise e to ln of x, the outcome is also x, and note that your x must be positive. So what about the derivative and the integral of exponential function? Remember that if you have e to the x and you take the derivative of e to the x, it's equal to e to the x. You can prove it using the limit definition of the derivative. If you have a function as an exponent, however, you have to use chain rule. You get u prime of x times e to ux. The integral of e to the x dx is the same as e to the x. Don't forget the constant of integration as well. Okay, let's take a look at this example. We are on the second page of 7.1. Example. Question says, hey, you have an integral which has e to the x dx on the numerator, and on the denominator you have e to the x plus 1. What is this integral? Well, here we have a quotient function. Look at the denominator. Suppose you set this equals to a new variable like u. So u is e to the x plus 1. What's the derivative of u? The derivative of e to the x is equal to e to the x, and the derivative of 1 is 0 dx. Okay, I have e to the x times dx, which is here. So I can rewrite this integral as du divided by u. We just learned that the integral of du over u or dx over x is equal to ln of absolute value of x plus constant of integration. So this integral is equal to ln of absolute value of u plus c, and u is equal to e to the x plus 1. So the integral is equal to ln of absolute value of e to the x plus 1 plus constant of integration. Now here's a question. Can I remove absolute value? Since e to the x plus 1 is always positive, we can get rid of absolute value and just write it inside this. Another formula for you. So far we learned that if we have ln of u of x, and we know that u of x is positive, the derivative is equal to u prime over u. But instead of ln, we have just log function. Log with base b of u of x, and you're taking the derivative of log. This is equal to u prime of x divided by u of x, and here you have ln of b. So you need to add a new concept, a new number, ln of b, on the denominator. Now for the integral of dx over x is equal to ln of absolute value of x plus constant of integration. And when you're taking the integral of b to the x dx, it's equal to b to the x. So you have your exponential function divided by ln of b plus constant of integration. If you take the derivative of both hand sides, since the derivative is the opposite of integral. On the left-hand side, you get b to the x. And the derivative of b to the x is b to the x times ln of b. So ln of b and ln of b cancel out each other. B to the x is equal to b to the x. Example A. It says find the integral of x times 3x squared dx. There you go. Here you have an exponential function. 3 raised to function x squared. You have a base, 3, and you have an exponent, which is a function. When you have an integral of this format, you look at the exponents. Let u be x squared. So what is du? Du is 2x dx. The derivative of x squared is 2x, and since you are taking the derivative with respect to x, you need to have dx. Well, look at your integral. You have 3 raised to u, you have x times dx. So if you multiply and divide your integral by 2, you can actually see du here. So multiply by a half and 2, 3 to x squared dx. This is your du. So this integral is equal to a half integral of 3 raised to u times d. Take a look at these two integrals. When you have integral of b to the x dx, it is b to the x divided by ln of b plus constant of integration. We have a half in front of the integral, and we have this integral, which by following the formula is going to be 3 raised to u divided by ln of 3 plus constant of integration. Note that our original integral is in variable x. So now that we have u, you use u equals to x squared to convert everything to x. You get a half 3 raised to x squared divided by ln of 3 plus constant of integration. This is your integral. Well, another example for you. B. So here you have the integral of 6 raised to minus square root of x divided by square root of x with respect to x, and x ranges between 1 to 4. Okay, very well. Here we have an exponential function, and the exponent is another function. So let u be your exponent, minus square root of x. So we're going to take the derivative of u. U can be written as minus x raised to a half. That's how to define a radical function. So du is equal to minus, we drop the exponent a half, and we subtract 1 from the exponent. So du is equal to negative a half x raised to minus a half. If you simplify this, we get minus 1 divided by 2 x to a half, which is negative 1 divided by 2 square root of x. Well, now look at your integral. This integral can be written as the integral of 6 raised to u. On the denominator, we have square root of x. What's missing? Negative a half is missing. So if you multiply this by negative 2, on the denominator you get minus 2 square root of x, and you have dx. This is your du. So here you have minus 2 integral of 6 to u du. Take a look at your formula, d to the x dx. This is equal to minus 2, 6 raised to u divided by ln of u, ln of 6 plus constant of integration. Our original integral is in x, so let's substitute that here. Minus 2, 6 raised to u, u is negative square root of x, divided by ln of 6 plus constant of integration. X ranges between 1 to 4. So let us plug in 4 minus 2, 6 raised to minus square root of 4 divided by ln of 6 minus 2, 6 raised to negative square root of 1 divided by ln of 6. So let us simplify this guy. Here you get minus 2, 6 raised to negative 2 divided by ln of 6 minus plus 2 times 6 to negative 1 over ln of 6. Here we can factor out 2 over ln of 6, so you get negative 1 over 36 plus 1 over 6. This is equal to 2 over ln of 6, negative 1 plus 2 divided by 36, 2 divided by 36, 1 over 18 times ln of 6. One last topic in 7.1, the tower function. How do we take the derivative of a tower function? The general approach to take the derivative of a tower function is like this. First of all, suppose you have a function of this format, tower function. Suppose you have y equals to f of x raised to another function like g of x. To take the derivative of this function, first of all, note that y prime is not equal to g prime of x, f of x to g of x minus 1. You cannot take the derivative this way. This is wrong. So what do we do instead? You can take ln of both sides, then start taking the derivative. ln of f of x raised to g of x, ln of y is equal to g of x times ln of f of x. Then you take the derivative of both sides. You get y prime divided by y equals to the derivative of g times ln. You have to apply product rule. So g prime times ln of f plus g times f prime over f. So this is the general approach. Then you multiply both sides by y, and the derivative of the function is equal to y, which is your tower function, times the derivative using the power function, using the product rule. Take a look at this example. Question says, take the derivative of the tower function y equals to x raised to 2x. One of the methods is to take the ln of both sides. So take ln. ln of y is equal to ln of x to 2x. Here you have exponent, write the exponent in front of your ln. ln of y is equal to 2x times ln of x. Now take the derivative of both sides. Take the derivative. The derivative of ln of y is y prime over y equals to. On the right hand side, you have the product of two functions, so you have to apply product rule. The derivative of 2x, which is 2, times ln of x plus 2x times the derivative of ln, which is 1 divided by x. Well, we can simplify this function. We can cancel out x and x. Y prime over y is equal to 2 ln of x plus 2. So the derivative of the function is equal to y times this expression. 2 ln of x plus 2. But what is y? Y is this power function, x raised to 2x. 2 ln of x plus 2. Well, let us move on to next topic. 7.2, which is exponential model, is going to be a discussion on Canvas. discussion on canvas. We're going to talk about hyperbolic functions. So first of all, let's define a hyperbolic function. Definition. Hyperbolic sine is defined this way. Hyperbolic sine of variable x is equal to e to the x minus e to minus x divided by 2. Hyperbolic cosine is defined this way. Cosine hyperbolic applied to variable x, which is e to the x plus e to minus x divided by 2. Very well, remember that how to define tangent. Tangent is equal to sine over cosine, and cotangent is defined as cosine over sine. So by dividing hyperbolic cosine and sine, hyperbolic sine and cosine, you can define your cotangent and tangent. So hyperbolic tangent, which is hyperbolic sine over hyperbolic cosine. The division between these two, we can cancel out the common denominator, which is 2. We get e to the x minus e to minus x divided by e to the x plus e to minus x. We can simplify this more. And cotangent, hyperbolic cotangent, which is defined as hyperbolic cosine over hyperbolic sine, is defined as e to the x plus e to minus x divided by e to the x minus e to minus x. We can also define hyperbolic secant and hyperbolic cosecant and the rest of the formulas. So let me list these formulas for you, then we go over some examples. Then we learn how to take the derivative, how to find the integral, and hyperbolic functions. Okay, let's write this here. Cosine hyperbolic e to the x e to minus x divided by 2. Hyperbolic tangent, we get e to the x minus e to minus x divided by e to the x plus e to minus x. And hyperbolic cotangent, which is e to the x plus e to minus x divided by e to the x minus e to minus x. First example on the first page. This question says, show that one minus hyperbolic tangent squared is nothing but hyperbolic secant squared. Well, to prove this equality, here you have left-hand side, you have right-hand side. You can start from left-hand side and show that left-hand side is equal to right-hand side, or you can start by simplifying right-hand side and show that right-hand side is equal to the left-hand side, or you can write both of these equivalently and show that after simplifying left-hand side and right-hand side, they are equal to each Very well. Let us start by simplifying left-hand side. Left-hand side is 1 minus hyperbolic tangent squared of x. We have a nice formula for that. 1 minus our hyperbolic tangent is defined this way. We have e to the x minus e2 minus x divided by e to the x plus e2 minus x, and we want to raise this guy to the second power. Perfect. So before raising this to the second power, can we simplify this more? Let me try to simplify this rational expression. I have e to the x minus e2 minus x divided by e to the x plus e2 minus x. So I have e2 minus x. I can factor out, or I can write it this way. E to the x minus 1 over e to the x divided by e to the x plus 1 over e to the x. Take the common denominator between these two. You get e to 2x minus 1 and e to 2x plus 1. And you can cancel out the denominators because both of them are e to x. So this is actually 1 minus e to 2x minus 1 divided by e to 2x plus 1 raised to the second power. Well, I have 1 minus, I can take the numerator, raise it to the second power. So I have e to 2x minus 1 times e to 2x minus 1 divided by e to 2x plus 1 times e to 2x plus 1. So this is equal to 1 minus, if you multiply these two, you get e to 4x minus 2 e to 2x plus 1 divided by e to 4x plus 2e to 2x plus 1. Let us take the common denominator between these two and simplify as much as we can. E to 4x plus 2e to 2x plus 1. And now I have e to 4x plus 2e to 2x plus 1 minus. Now I have to distribute this negative sign for this expression here. Minus e to 4x plus 2e to 2x minus 1. Well, let's simplify this. I can get rid of e to 4x, e to 4x. I can get rid of 1 and minus 1. They are opposite of each other. What do I have here? I have 4e to 2x divided by, and if I write this in compact form, I get e to 2x plus 1 raised to the second power. So this is my left-hand side. My left-hand side is equal to 4 e to 2x divided by e to 2x plus 1 squared. Take a look at your hyperbolic secant squared. Hyperbolic secant squared is 1 over cosine hyperbolic x. And it has exponent 2. So I'm going to flip my hyperbolic cosine and raise it to the second power. This is equal to 2 over e to the x plus e2 minus x raised to the second power, which is equal to 4 divided by e to 2x plus 2 plus e2 minus 2x. If we write this with positive exponent, we have 4 divided by e to 4x plus 2 e to 2x plus 1 divided by e to 2x, so you can flip it and write it as e to positive 2x, which is equal to 4 e to 2x divided by, if you write this in compact form, you get e to 2x plus 1 squared. Left-hand side, right-hand side, both of them are equal to each other, so we just prove that these two are equal. So let's define the derivative and the integral of these functions. The derivative of hyperbolic cosine is equal to hyperbolic sine. The derivative of, so let's write the integral as well. The integral of hyperbolic sine with respect to x is equal to hyperbolic cosine. Don't forget the constant of integration. The derivative of hyperbolic sine is equal to cosine, hyperbolic cosine. There is no negative sign for the derivatives. It's not the same as the sine and cosine. Remember how we define these functions. It's exponential function. So the integral of hyperbolic cosine is equal to hyperbolic sine, constant of integration. The derivative of tangent, hyperbolic tangent, is hyperbolic secant squared and the integral of hyperbolic secant squared with respect to variable x, of course, equals to hyperbolic tangent, constant of integration. Then the integral of, hyperbolic cosecant. Let's go. So you know that the important one is the derivative of hyperbolic secant is equal to secant tangent, and we have a negative sign. Okay. So when you take the integral of secant tangent, dx, it is minus hyperbolic secant. Constant of integration. Important formulas. You can prove all of these using the definition, exponential definition. Example. So in this example, here we have a hyperbolic secant, 3x, and the question says, take the derivative with respect to variable x. Very well, we have to apply chain rule here because you have 3x, it's not just x. So take a look at your hyperbolic secant, the derivative. This is equal to, first of all, you have to put a negative sign in front of the derivative of 3x is 3. Then you copy down your hyperbolic secant times hyperbolic tangent of 3x. Pretty much following the formula and applying chain rule because of 3x. So this is part A. Part B says, take the second derivative of this function. Take the second derivative of hyperbolic secant 3x. So to take the second derivative of this function, we have to use its first derivative. It is the derivative of negative 3 secant hyperbolic secant 3x times hyperbolic tangent 3x. We are taking this derivative. Here you have the product of two functions. You have to apply product rule. So, first of all, you have a constant. We can write down the constant in front of the product rule. Minus 3, the derivative of hyperbolic secant times hyperbolic tangent plus hyperbolic secant times the derivative of hyperbolic tangent. We have product of two functions. We have to apply product rule. Well, the rest is not that hard. You have all the formulas that you need. This is minus 3. The derivative of hyperbolic secant 3x, we already calculated that. This is here. It is negative 3 hyperbolic secant 3x times hyperbolic tangent times hyperbolic tangent, so you have to have exponent 2 plus, here you have hyperbolic secant 3x, and now you have to take the derivative of hyperbolic tangent. You know that hyperbolic tangent derivative is equal to hyperbolic secant squared, but note that here you have 3x, so you have to apply chain rule. It's going to be 3 times hyperbolic secant squared of 3x. Write this in bracket, since I use bracket here. Very well, the rest is just algebra, finding similar terms, combining them. Here we have hyperbolic secant raised to the second power. So if you combine these two, you get hyperbolic secant raised to the third power. Here you have distribution of minus 3. You get 9 secant hyperbolic 3x times hyperbolic tangent squared of 3x minus negative 3 times 3 gives you minus 9 hyperbolic secant of 3x raised to the third power. Here you can factor out hyperbolic secant and simplify this more. Well, you can write it as 9 hyperbolic secant 3x. You're left with hyperbolic tangent squared of 3x minus hyperbolic secant to the exponent 2. So write this a little bit further here. And this is your final